a quick review of last class's work. So we said we are going to use it's quite common to use a MOS varactor to do the tuning of the VCO, and it's quite common to have specialized MOS varactors so that you have monotonic tuning. Okay. For example, this shows the accumulation varactor. Okay, where you modify the device slightly without changing your overall semiconductor process. You modify the type of device to make sure you get what you want, right? Then we said we are going to compare the cross-coupled NMOS only oscillator or PMOS only oscillator with the complementary cross-coupled oscillator. So we said, okay, so the first things which are common to the two, the cross-coupled pair or pairs switch at the oscillation frequency f0. Number two, the positive feedback due to this cross-coupling makes the switching very fast, right? Because you are going to apply strong positive feedback because you want the circuit to start up very quickly. Okay, and okay, so we said we can analyze it in a certain manner. You replace the cross-coupled pair with a switching current source. Extract the Fourier series, the fundamental component of the Fourier series, that gives you the fundamental current that gets multiplied by the impedance of the RLC tank to give you your output amplitude. And as it turns out, for the NMOS only oscillator, the output amplitude ends up being 2ITR by pi. The output amplitude is 2ITR by pi. If you look at the complementary cross-coupled oscillator, the behavior, the way the current flows is slightly different, right? That much should be pretty obvious, because in this case, current is actually flowing through the RLC tank during the complete RLC tank during both halves of the cycle. That is the difference between the NMOS only and the complementary oscillator. In the case of the complementary oscillator, half the tank was carrying the full current for half the time. Here the full tank is carrying the current in two different directions, in two different half cycles. And therefore, if you actually look at the overall amplitude of the complementary oscillator, it is actually twice what you get from the NMOS only cross-coupled oscillator. Okay, so then we moved on to another important aspect, in fact very important aspect of the oscillator, which is phase noise, right? The reason we actually progressed in this manner is because we said for the same current you get twice the amplitude for the complementary oscillator. But why are we worried about amplitude? Because really in the mixer you want any specific amplitude, but you know, if you want, let's say 1 volt peak to peak at the mixer, the VCO can still generate maybe 500 millivolts and you can just gain it up, right? That's really just a matter of giving in more current, right? So what is the significance of getting more amplitude? In fact, inside the mixer, we discussed this last time, you look upon the LO signal as simply a signum function, right? It just switches the current, right? And if the sinusoid is large enough, it will completely switch the current, and quite quickly also. So the amplitude itself is not particularly significant. In the examples we took, which are switched mixers, whether it's active or passive mixers. Obviously there are other kinds of mixers where the LO amplitude could be significant, but we did not consider them because they are not very commonly used in IC design. Okay, so as it turns out, the amplitude of the oscillator is intimately tied in with the noise performance of the oscillator. Okay, what kind of noise are we talking about? So we said because we don't worry too much about the amplitude at the mixer is interested only in the zero crossings. Therefore, we are primarily interested in imperfections in the zero crossings at the VCO output. Okay, and more importantly, we are very interested in knowing about random imperfections. There may be a systematic imperfection. Maybe there is some imperfection maybe there is some duty cycle error. There can be some systematic duty cycle error which will cause some systematic problem. But the random problems will be even more significant. Okay? In the time domain, obviously these random zero crossings will have a particular effect. and this is called jitter in the time domain. In the frequency domain, we call this as phase noise. Okay. Now, obviously the two are practically equivalent, except in the way that we use them or analyze them or conceive them. So in other words, jitter is measured in a certain manner, maybe maybe some statistical quantity, right? And phase noise may be measured in a slightly different way in this frequency domain. But there is a way to go back and forth between the phase noise and the jitter. Okay? Like I said, in the time domain, this will be manifested as imperfections in the zero crossings. In the frequency domain, we said an ideal oscillator will just look like a cos omega naught t, so you will get two impulses at plus or minus omega naught. Okay? If you have a non-ideal oscillator with phase noise, okay, that will manifest as phase sideband or frequency sideband. Okay? Because the phase noise will naturally get transferred to frequency. There is a definite relationship between phase and frequency. And if you take any practical oscillator and look at its output spectrum, you will see these noise sidebands. Hopefully, the noise sidebands will be limited and will have a certain shape that we can understand very well. Now you notice that I have actually drawn it in a particular manner, right? Why have I drawn it in this way? I have drawn it as if it is like very high, as you get closer to the oscillator, maybe much lower. Why do you think that is? Intuitively, so far you don't know anything about phase noise, right? So can you imagine a reason why it could look like that? We are designing for F0. Okay, so what? Okay, that's fair enough. So you could say you are trying to get F0, so that should be a dominant quantity, right? So the phase noise at other frequencies should be low. I mean, for example, if you had a phase noise which looks something like this, obviously it's no longer an oscillator. This is just broadband noise, right? So it should look something which looks like an oscillator. Fair enough. Anything else? Okay.
So you can argue that noise from the current source gets translated to the.
Okay.
So the current source has a sort of different.
Fair enough, right? So let's say the current source had a combination of flicker noise and thermal noise. So let us. So now we are getting into the details, right? So I'll draw only the positive side for now. So ideal LO looks like this, and I said the practical thing will look like this. Okay? So we are trying to understand why the blue curve exists and why it would have this kind of shape. So there are several reasons given. So one reason given is, so it should look something like an oscillator, right? So that kind of makes sense. The second reason given is mixer action. Okay, from tail current source to output, right? So let us look at that. So what he says is, we'll take the cross-coupled NMOS only cross-coupled pair, but it doesn't matter really. So I have some IT plus some noise here, correct? What kind of noise? I'll have device flicker noise and device thermal noise. Okay, so if I actually look at IN here, okay, or the, let's say, magnitude of IN, what is that going to look like as a function of frequency? I'll have 1 over F noise, and at some point of time I'll get thermal noise, correct? So I'll have I'll have 1 over F noise and thermal noise, correct? So if I actually look at this this cross-coupled pair, it's acting like a mixer. If I really had built a mixer, the noise from the transconductance device would go to the output. We have already seen that before. So maybe the noise from this baseband device also goes into the output. That is also possible. Okay. How will that appear at the output? It will get upconverted, multiplied by some omega naught. So instead of having flicker noise around DC and then thermal noise, what you would actually expect at the output is around F naught. You would maybe expect 1 over F and flicker and thermal. Maybe you might expect something like this. Okay, around F naught you may expect to have 1 over F and thermal, so you may get that shape. Anything else? Any other reason? We will see if each of these is true or not. Okay, we are going to look at each of these in detail. Any other reason why it should have some shape like this, where it's very much larger close to F naught and much smaller elsewhere? That's a very basic reason. Exactly. So the parallel RLC tank has a very strong frequency response, right? That we have assumed right from the beginning, that it has a resonance at omega naught. Okay. Even when the current has a switching component, we have looked at the component only around omega naught. We have assumed it filters out everything. Now, the amount by which it filters out of frequency components away from omega naught is defined by what quantity? By the Q of the RLC tank. Okay. If you have even decent amount of Q, maybe 10 or 15, you will be suppressing this noise very well. Okay. Even if you were to put in broadband thermal noise into the tank, okay, the tank will shape it into something which looks like the blue curve. Okay, that is the third and very important reason why the noise skirts are expected to look like this. Okay. So there is a third reason, and I'll put it up here. Okay, the frequency response of the RLC tank. Okay, so these are three reasons why you expect the noise to be higher at as you get closer to omega naught, because you get lesser and lesser separation from the tank. As you get further out, you expect it to be very good. Okay, so far so good. Now, suppose you have a disturbance, okay, which is being, or let's say you have some noise from the circuit which is actually disturbing the oscillator. Now we are interested in something which disturbs the phase of the oscillator. Okay. So we need to understand what sets the phase of an oscillator. So what sets the phase? So if I actually build an oscillator, a cross-coupled oscillator which looks like this, what sets the phase, the output phase? The initial condition. Anything else? That is pretty much it, right? There is nothing else in the circuit which actually sets or operates upon the phase of the oscillator. There is something which operates on the frequency, but if you but through the control voltage. So indirectly you could say there is some effect on the phase. But if you take just a standalone oscillator, okay, there is nothing which actually directly sets the phase. So if I look at the phase of an oscillator, okay, in fact, let us say I plot theta versus time. What will that look like for an ideal oscillator? It will increase linearly, right? Maybe something like this. I'll just do this. Okay. If I actually take a practical oscillator which has noise, what do you think that will look like? That will, of course, deviate from this linear phase. Okay. Will it do this? Will it do this? What do you think it will do? So if you look at the phase deviations caused by any of this noise, what do you expect in the long term? What do you expect these phase deviations to be? Correct. They should average to 0, right, or close to it, right? So more or less, they shouldn't take you in any systematic direction, but they will operate on the phase of the oscillator. So what you really expect are neither of these guys. Okay, so you actually expect maybe something like this, right? Which may overall take you along the same path as you as an ideal oscillator, but there will be deviations, short-term deviations, right? Over the long term, it should stick to the same characteristic. That is what we know. Okay. Okay. So, because there is nothing else inherent inside the oscillator which operates on the phase, okay, we have to be very careful about any noise injected into the oscillator which changes the phase of the oscillator, right? Obviously, the phase of the oscillator is an important characteristic because the phase directly decides the frequency of the oscillator and the frequency response. If you look at the output, you don't want to see these frequency sidebands. Okay. Now, if you look at the way this phase noise is measured, okay, there is something called the single sideband phase noise, which tells you, which defines phase noise of an oscillator. Okay, because there are really many ways to define noise. Okay, you can define it as a signal to noise ratio, a noise to signal ratio. You can define it as raw noise, voltage noise, current noise. There are really many ways to define it. For an oscillator, there is one accepted standard way of defining it when used with a wireless transceiver. Okay, again, it is defined in this particular way because of the application. You could take the same oscillator, define it in the time domain as jitter, for example. Okay, so if you look at an oscillator, so let us say this is the, or let me draw it in a slightly different way. So this is the frequency, this is the ideal F0 that you want, and let us say the noise skirts look like this. Okay, these are all terms which you will see very often. Noise skirts, I mean, it should be pretty obvious, right? So don't ask me to explain like many of these terms because they are pretty obvious. Okay, so these noise sidebands or noise skirts are decreasing with frequency, and at a particular offset delta f from the oscillation frequency f0. Okay, so at an offset delta f from f0, I am going to take a slice of 1 Hertz frequency. Okay, in other words, a unit frequency slice at an offset delta f from the oscillation frequency. I am going to take the slice and integrate the noise around it, noise under it. Okay, so if I do that, okay, that will give me an idea of the noise behavior, the noise spectrum, as a function of the frequency offset from your oscillation frequency, right? This will have a dependence on delta f, obviously. That itself, the noise curve should tell you that, right? The noise curves tell you that this particular noise at an offset delta f should be a function of delta f. Okay, we are going to see soon exactly what form this takes, but it should be a function of delta f. Okay, and it's quite common to express the phase noise as using the term L, or the more Latin or I guess more artistic form of L, maybe something like this. Okay, but it's a lot easier for me to just use L. So L of delta f is 10 log of, so it's represented in some kind of dB terms, 10 log of the power in this 1 Hertz bandwidth at f0 plus delta f, okay, over the signal power. So remember yesterday I said it is represented as some negative SNR dB, or noise to signal ratio, right, is what we should have said. So what I meant is this noise to signal ratio. Okay. And so you take it as 10 log of the noise power over the signal power. Okay? So this is how you represent the single sideband phase noise of an oscillator. The lower the noise, right, the lower this quantity, the better the oscillator, right? If I take the same oscillator and I have larger signal power, this automatically means that the phase noise is lower, because you are comparing it with respect to the noise power to the signal power. Now you understand the significance of why the complementary cross-coupled pair is better. You have similar noise sources coming from the transistors and the tank. You have normalized everything else, but you get twice the amplitude. So everything else being the same, so if I take this oscillator versus this oscillator, I have said I am going to normalize for the tank, the same RFIC tank. I am going to normalize for the same current IT. I am going to normalize for the same startup gain. So the overall GMs from the active devices are the same. So the noise sources are almost identical. They are not exactly identical, but they are almost identical. But one has twice the amplitude compared to the other. So in terms of noise to signal ratio, the complementary pair is much better for a given current. Is that understood? Okay. What are the units of this phase noise? So as it turns out, it is given as dBc per hertz. It should be dBc. What is dBc? dB is with respect to the carrier. Okay. There is a per hertz added to the unit to indicate that you are integrating over a 1 hertz over a unit frequency. Okay. So the idea is at any offset you are comparing the power to the carrier power. Okay. Expressing it in terms of dB, and you are looking at the density, the noise density. Okay. So it's expressed in dBc per hertz. Okay. Now, before we go on to decide what this exact expression for phase noise is, how does it affect us in a transceiver? So we need to look at the effects of phase noise before we decide why we want low phase noise. Okay. So let us take a simple mixing action. Okay. So this particular effect is called reciprocal mixing. Okay. So suppose I have an ideal LO, okay, which is being mixed with the desired RF signal. Okay. To translate the signal down in frequency in a receiver. So let us say it goes to some maybe some IF frequency. Correct? All well and good. Let's say I have a large interferer here. This is some large interferer. What happens when I add the interferer? The interferer will also get translated down. Correct? This is what would happen in any normal transceiver. Now, I'm just going to make a copy of this thing. Now what I want to see is, instead of having this kind of LO, okay, I am going to have an LO which has these side bands. Correct? I am going to multiply it with an LO which has these side bands. What is going to happen? So of course, this, first of all, the desired RF signal is going to get these side bands also. Okay, the minute you multiply with the LO, any noise sidebands around the LO will get transferred onto the IF signal. More importantly, okay, so you're going to have sidebands around the interferer. Okay, if the interferer is, the dynamic range between the interferer and the desired RF signal is very large, right? In other words, maybe the interferer is maybe 40-50 dB larger than your desired RF signal. What happens? The phase noise skirts around the interferer can completely drown out the desired RF signal. Okay, so this particular effect is called reciprocal mixing. Is that clear to everyone? Okay, now let us take another example. So let us say I am transmitting at a particular frequency. This is my TX, and I told you many of these systems use frequency division multiplexing. So frequency division duplexing. So inside the same transceiver, the receive frequency is offset from the transmit frequency by a certain amount, maybe a few tens of megahertz. Okay, so let us say you are trying to transmit a very large signal, right? Maybe 20-30 dBm, maybe 1 watt. The receive signal you are trying to receive is maybe microwatts. Okay, maybe even much smaller. Okay, so maybe the receive signal is much smaller. Okay, if you have ideal LOs, everything is fine. Ideal LOs inside the transmitter and the receiver, everything looks fine. They are very well separated in terms of frequency. If your transmitter LO has phase noise sidebands, what happens? The phase noise sidebands of the transmitter could completely drown out your received signal. Okay, so this is another effect of phase noise. A powerful TX so in the presence of phase noise, a powerful transmitter could completely drown out your own receiver. You could also drown out somebody else's receiver. Okay, both of these are possible. What else? If you have some kind of modulation scheme where you depend on keeping certain frequency components separate. So obviously what is happening is, the original with an ideal LO, you keep all the frequency components separate. The minute you have phase noise, they are all getting mixed up, right? For example, if you look at OFDM, okay, OFDM relies on the fact that you have a whole bunch of subcarriers, okay, which are very well separated, which are completely orthogonal. Okay, the minute you add phase noise, okay, what happens is all of these start to get mixed up. Okay, so you get some subcarrier interference inside OFDM, and that could completely destroy the signal that you are trying to transmit or receive. Okay, so all of these effects are possible only in the presence of phase noise. Yes.
These requirements aren't they set up by spectral mass? Spectral mass will define how much power you can transmit.
Correct. Correct.
So doesn't that take care of this problem?
No, what do you mean by take care of this problem? If not for the presence of phase noise, you would very easily meet your spectral mass. The spectral mass is the requirement, right? This phase noise is the overall cause of why your RF signal could actually be drowned out. If not for if not for the presence of this phase noise, what else could actually cause a problem at your receiver? Yes, you could have a linearity problem, but if the receiver is, let us say let us take the example of let's say a GSM signal. Okay, the signal is only at bandwidth is only 200 kilohertz. Okay, you are talking about spectral mass at maybe 20 megahertz away. Okay, which is actually quite far away compared to your signal bandwidth to actually cause any major problems due to linearity. Bigger problems will be actually be due to phase noise rather than linearity. Okay. It is called reciprocal mixing. Actually, I'm not sure. I'm not sure actually. Probably because you're mixing two things, but yeah, reciprocal mixing doesn't make sense. So yeah, I'm not sure. Okay. So obviously phase noise is a huge problem in any of these transceivers. Okay. So this should give you an idea of why phase noise is important. Now, so far we have defined phase noise. We have seen why it is important. Now we need to analyze and see what is the actual behavior of phase noise as a function of frequency offset. Okay. So we'll take two approaches to this. Well, what we'll do is we will first try to pick up the old the simpler LTI model for noise, okay, which is obviously not complete. We will try to build up a phase noise model out of it and try to see whether it matches with what you actually observe in an oscillator. So this is the history of oscillators actually, right? So what they would have done was, the first people who built these things, they would have built the oscillator, stuck it into a spectrum analyzer, try to look at the frequency components, try to look at the sidebands. They will observe a certain thing. They will try to come up with an LTI model. Unfortunately, the LTI model was not good enough to explain, so you need to understand even better. And as it turns out, people have built up even better understanding of what processes actually lead to this phase noise and have more accurate expressions for this. Okay, we will look at the LTI model because it's obviously very easy to understand. Okay, we will look at so there are other models. People have tried applying non-linear but time invariant models, okay, or non-linear but time invariant analysis to VCO phase noise, okay, and people have actually applied linear but time variant analysis to phase noise, okay. So in your, I guess, opinion, or based on what you have seen so far, what do you think, which one of these theories, either LTI, NLTI or LTV, which one of these theories do you think will be most accurate and why? Because the mixing action, okay. 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 So fair enough. So he says that because there is some noise happening due to mixing action, we have already seen that mixers are time variant systems. So it seems like the LTV analysis seems most appropriate. Would you need to apply some kind of non-linear time variant analysis? Okay. Okay. What else? Anybody else?
Very important processes. There are cases when the factor behaves non-linear. Actually, I think that will give more accurate expression.
Okay.
One more thing is the reactor.
Okay. Correct. Okay. So fair enough. So so some people say that, yeah, like one of you has said that the varactor is non-linear, so you have to take that into account. Then he said that the signal swings are becoming large fractions of supply voltages and the device is inherently non-linear, and so on. So definitely all of these things are valid. Now the fundamental thing you have to understand, okay, is two things. So first of all, when you do noise analysis to figure out the overall output noise, what do you do? Correct. So first of all, based on what we know from normal circuit theory or circuit analysis, we have a linear small signal model for the overall circuit, and we apply that to actually find out maybe overall input referred noise or output referred noise, and then figure out what the noise behavior of the circuit is. Correct? We compare that with the small signal gain of the circuit. The reason is many of these analog and mixed signal circuits are small signal amplifiers or small signal circuits. So it is perfectly fine to do that. The minute you have circuits like oscillators, mixers and so on, they are no longer small signal circuits. They no longer have a very the DC you cannot define something called a DC operating point. I mentioned this last class. You have what is called a periodic steady state or a periodic operating point for the circuit. Okay. However, if you look at the noise in the circuit itself, the noise itself is expected to be much smaller than the signal or the DC operating point. Okay. So the way you should look at the circuit really is that as far as the signal is concerned, obviously the system is non-linear. You will have to actually find out, use some kind of periodic steady state or periodic operating point to figure out the signal behavior of the circuit, as well as to figure out what gains you have from different parts of the circuit to the output. Okay. However, around this periodic steady state point, you can actually linearize the circuit and apply this linearized gains and transfer functions to noise. Okay, because the noise itself is a small signal and you can apply some kind of linearized behavior on noise. Okay. Now the time variance part is obviously critical because the time variance leads to noise being translated from different frequency bands to your desired frequency band, and that definitely does happen here as in the case of mixers. Okay. So the true way to look at it is, as far as noise is concerned, okay, you are going to do some kind of linear time variant analysis. So as far as the signal is concerned, you are going to do some kind of non-linear time invariant analysis. Okay, because if you didn't have noise, for example, the signal itself, the system itself can easily be analyzed using large signal analysis. Okay, so these two things we have to understand. Now, obviously, the dominant effect which makes the VCO different from other kinds of linear circuits is the fact that you, similar to mixers, you have noise being folded down from many frequency bands onto your desired frequency band. Okay. Now, frequency translation can happen either due to nonlinearity or time variance. Okay. This is why you will see, if you go back and look at the history of oscillator noise, you will find people have tried applying nonlinear analysis as well as time variant analysis. Okay. So both of these are possible to varying degrees of accuracy. The latest accepted way of analyzing this is using time variant analysis, which also seems more intuitive. What we will do is, probably the analysis of that will probably be too much for this course. We will do the LTI analysis. I'll give you, maybe we'll spend one class on the time variant analysis. Okay. But probably we won't get into a lot of detail. Not even as much detail as we got into mixers, because we need to move on and do other things in this course also. Okay. I'll give you the references. You can go ahead and look it up. Okay. Yes. Okay. Okay. Good question. So, what kind of time variant effects do you expect as far as the signal is concerned? Mixing. Okay. So that's what I'm asking. So even in the mixer, the time variant behavior was between certain ports, not between all ports. There were, if you look at mixer is a 3-port device. So you have the let's say the RF port, base LO port and IF port. Okay. If you take pairs of ports and look at the transfer functions between these, some of them are nonlinear but time invariant. Some of them are, time variant. Okay. In the case of the VCO, okay, so let us look at the signal behavior. So do you expect some kind of time variant behavior? And if so, what? What kind of time variant behavior do you expect? in the absence of noise and assuming that the circuit is perfectly symmetric, there is no need for any time variance analysis. Okay? Okay. Correct. There's no input signal at all, really. Okay? Okay. So the first what we'll do is we'll look at LTI analysis of noise. Okay? Now noise in oscillators. Okay? Very specifically, there is a famous paper by D.B. Leeson. It's called a simple model of feedback oscillator. Noise spectrum. Okay? And it's published in the proceedings of the IEEE. Okay? Pages 320 to 330 in February 1966. Okay? So you can imagine how far back you're looking at. People have looked at these issues. Right? Obviously people have always known that noise was a problem, and the day you start building a communications transceiver and you start testing it in the presence of interferers, you will probably find out these effects. Right? So this has obviously been a long-standing problem in oscillator design. Okay? Now what we'll do is, to move forward with this analysis, we are going to do certain very simple things. Okay? So first of all, okay, so we'll take this RLC tank. That is obviously an LTI system. Correct? The RLC tank is obviously an LTI system. It's composed of purely passive linear elements. Okay? So we'll take this guy. Now outside this we have the active portion of the system, of the oscillator. Now the active portion itself is obviously nonlinear, right? We have a switching transistor and so on. However, to linearize an analysis, what we'll do is this, right? So we'll say it has some system which actually restores the energy lost in the tank. That is what we know. Okay? However, what we'll also do is, we'll say there is some noise represented by some IN squared by delta F. Okay? Which is being fed into the RLC tank. Okay? And we'll say this is a noiseless energy transfer block. Okay? So for now, we'll pull out the energy. In fact, we will even assume, let us, to start off with, we will assume that IN squared by delta S comes completely from thermal noise. Okay? It could be thermal noise from the transistors, it could be thermal noise from the resistors, but we'll just say it's thermal noise. Okay? We will look at other effects later. And the noiseless energy transfer happens from the other one. Okay? So now, how would you analyze this particular network for noise? Okay, good question. So if you do this, this will give you the output voltage noise. So he has a very pertinent question. Are we interested in the voltage noise or the phase noise? What do you think? It's a very pertinent question, right? So far we have been talking about something called phase noise, but suddenly I am saying, take the current noise and multiply it with the voltage and so on, right? So what's the problem? It's possible that the two of them are linked. Okay, correct. So let us take any noise source, right? So let us say we have a noise at a pair of nodes. Let's say differential pair of nodes. Okay. So I take a resistor. Okay, and I have Vn squared between these two nodes. Okay. What kind of noise is this? Is it amplitude noise, phase noise? What is this? So rather what we are asking is the noise in the amplitude or the phase of the signal we are observing between these two nodes or between any two nodes? Okay, we can talk about it in the time domain.
When you take a Fourier transform, there will be some amplitude component and there will be a phase.
Correct.
So, when you both the noises are present,
Right? Exactly. So if you look at any noise, so obviously in the time domain it is some kind of variation. Okay, some kind of random variation. If you look at the frequency domain, okay, there are two characteristics to any signal in the frequency domain. You have the amplitude and you have the phase. Obviously these time domain variations will cause some impact on the amplitude of the signal and some impact on the phase of the signal. Okay? How much impact on amplitude and how much impact on phase? Depends on the what instant we are depends on what instant we are injecting the noise. Okay, that's right. But that is not what I am asking. If I just take any signal, so let us take a resistor, right? I have some Vn squared. What is Vn squared? 4 kT R delta F. Correct? I know the noise of a resistor is 4 kT R delta F. So if you had to figure out how much of this noise is in the amplitude and how much of this is in the phase. Correct. Correct.
The phase noise you can't talk in terms of voltage record because it's a variation.
Correct.
So it is something like radius per.
Sure. That's right. That's okay. So in fact instead of phase noise I can look at the I can actually define phase noise even for a resistor in terms of this. Can I define this even at the output? I can't because now I don't have a signal. But suppose I had a signal in series with this, I could actually define it in this manner, right? So what do you think? Okay, so why don't you think about it? We'll discuss it first thing on Friday's class. Okay?